Hello everyone, and thank you for attending my virtual presentation. I'm Christos Moussas from Purdue University, and I will present you my research entitled Real and Virtual Environment Mismatching Induces Arousal and Adult Movement Behavior. Experiencing a virtual environment while being in a constrained real environment might be problematic. Moving within that real environment while wearing a head-mounted display may alter the psychological state of participants due to the mistrust of the real environment. In general, constrained real environments provide different challenges compared to virtual reality lab spaces. For example, in home or office virtual reality setups, the furniture constrains the walkable area, whereas virtual reality labs are typically large empty rooms. Despite the fact that a number of mapping and fit techniques have attempted to solve the mismatching problem, further experimentation is required in order to assess how deviations between virtual and real world may affect the psychology and movement behavior of participants. It has been found that the conflict between the provided visual stimuli of the virtual environment and the participants' knowledge of the real environment in which they are situated affect their navigational choices. However, even though we do know that aesthetically mismatched real and virtual environments alter movement behavior in virtual reality users, less attention has been given to the user's psychological state. Therefore, more input is required on the exact type of mismatches which are responsible for affecting mental and physical behavior. Understanding the way alterations occur in arousal and movement behavior when interacting within such environments can yield several beneficial applications which can prove useful for virtual reality developers. This paper investigates whether and what type of mismatches between a real and virtual environment might affect the electrothermal activity and movement behavior of virtual reality users. As a task, participants were asked to walk around the environment by simply following a provided path. Based on the collected data, this study aims at answering the following four research questions. Are there differences in the electrodermal activity of participants across the five experimental conditions? Are there differences in the movement behavior of participants across the five experimental conditions? Are there differences in participants' behavior when interacting with completely mismatched environments compared to partially mismatched environments or identical environments? Does arousal correlate with the movement behavior of participants when working with mismatched real and virtual environments? For this study, 100 healthy individuals were recruited from a university setting. The participants were recruited through posters placed on notice boards across campus, class announcements, and emails. All participants were volunteers and there was no type of compensation involved. Of the sample size, 31 were female and 69 were male. 38 had no prior experience with virtual reality. Moreover, none of the participants experienced motion sickness during the experiment. Note that participants were provided written consent as dictated by the ARB of our university. This study was performed at the motion capture studio of our department. The dimensions of the studio are 8 meters long, 8 meters wide, with a ceiling height of 4 meters. These dimensions were used to approximate the design of the virtual environment used in the study. We removed all furniture from the lab to be as empty as possible. For the purpose of this experiment, two different environments were designed. The first one was a replica of the motion capture studio that was used as our baseline environment. The second one was an imaginary environment that was designed to let us investigate the alterations of human electrodermal activity and movement behavior. We developed 5 experimental conditions to help us understand how and if participants' prior knowledge of special constraints in the real environment could alter their arousal and movement behavior when they were immersed in a virtual environment. The developed conditions were the following. The first condition is called matched appearance and no constraints. This is our baseline condition. The virtual environment in this condition is a replica of the real environment in which the experiment was conducted. This baseline condition was used in order to capture the way that participants move and respond in a constrained environment condition. No obstacles were in either the real or virtual environments during this condition. The second condition is called mismatched appearance and no constraints. This condition presents an imaginary environment that matches the spatial constraints of the virtual environment. No obstacles were in either the real or virtual environments during this condition. The third condition is called mismatched appearance with constraints. This condition uses the imaginary environment and there is mismatching of the appearance between the real and the virtual environments. Spatial constraints were added in the real environment by placing obstacles such as curtain boxes and a notice board. Obstacles did not show in the virtual environment. However, note that participants were aware of the obstacles as the obstacles were placed there before the start of the experiment. The fourth condition is called mismatched appearance and match constraints. This condition uses the imaginary environment, and the obstacles in the real environment are substituted with the virtual objects in the virtual environment. Note that the size of the objects in the virtual environment match the size of the obstacles in the real environment. Moreover, as the mismatch appearance with constraints condition, the participants of this condition were also aware of the obstacles placed in the real environment. The last condition is called mismatch appearance and mismatch constraints. This condition uses the imaginary environment, and there is mismatching of both the appearance and the spatial constraints between the real and the virtual environments. The spatial constraints mismatching was achieved by placing obstacles in the real environment. Specifically, the position of obstacles in the virtual environment do not match the position of obstacles in the real environment. Note that participants were aware of the position of the real obstacles as the obstacles were placed in the real environment before the start of the experiment. The devices used for this study were the MSI VR1 backpack computer for running the virtual reality application, the HTC Vive Pro head-mounted display for projecting the virtual reality content, the XS motion capture system for transferring the motion of participants with the virtual environment and for capturing their motion, and finally the Simmer 3 GSR Plus 1 electrodermal activity sensor was used for capturing the physiological responses of participants. The application used for the study was developed in the Unity 3D game engine version 2019.1.4. In this study, regardless of the condition our participants exposed, all of them were asked to follow the exact same path. Note that the total distance participants had to cover was 150 meters. The rationale for choosing such a long walk was based on our assumption that even though participants were aware of spatial constraints in the real environment, after walking through various positions within the virtual environment, they would expectedly become unaware of their spatial position with respect to the obstacles. This sense of disorientation is what we want to induce to our participants during the study to investigate possible alterations in their arousal and movement behavior. The path course would appear progressively on the ground in the form of a rendered line that the participant would follow. We decided to have a line displayed on the ground. Our intention was to examine how closely participants would adhere or how far they would deviate from the specified course. In designing the predefined path, we considered the proxemics model. The minimum distance between the points of the path and obstacles or walls was set as a distance of 23 cm. Note that the diameter of the far face of the intimate space is 46 cm. Based on this, we made sure that all participants had enough clearance to move relatively comfortably within the virtual space. Electrodermal activity and movement behavior data were collected to investigate possible variations in the participants' behavior during the experiment. To record the electrodermal activity, we identified and calculated the number of peaks and their average amplitudes throughout the experiment. These procedures enable us to examine both the frequency and the intensity of physiological arousal in the participants. A motion capture system was used to record the movement behavior of participants under the assigned experimental conditions. Our goal was to get both global and local input on how participants walked within the virtual environment. To obtain global input, we captured the average speed of the participants and the average deviation from the provided path. These measurements provide spatiotemporal information about the participants' movement behavior. To obtain local input, we computed step length and step duration. A one-way analysis of variance was used to analyze the data using the 5 conditions as a dependent variable and the collected data as dependent variable. No significant results were found with respect to the number of peaks. However, we did find significant results in the participants' amplitude of peaks across the 5 experimental conditions. Pairwise comparisons show that the mean amplitude of peaks during the mismatch appearance and no constraints condition was significantly lower than that for the mismatch appearance with constraints condition and the mismatch appearance and the mismatch constraints condition. Moreover, the mean amplitude of peaks during the mismatch appearance and no constraints condition was significantly lower than that for the mismatch appearance with constraints condition and the mismatch appearance and the mismatch constraints condition. Regarding the movement behavior feature that described the global motion of participants, we found a significant effect of participant speed across the 5 experimental conditions. Pairwise comparisons shown that the mean score for the matched appearance and no constraints condition was significantly higher than that for the mismatched appearance with constraints condition, the mismatched appearance and constraints condition, and the mismatched appearance and mismatched constraints condition. We also found a significant effect of the participants' deviation from the provided path across the 5 experimental conditions. Pairwise comparisons shown that the mean score for the mismatched appearance with constraints condition was significantly lower than that for the mismatched appearance and no constraints condition, the mismatched appearance and no constraints condition, and the mismatch appearance and mismatch constraints condition. Moreover, the pairwise comparison showed that the mean score for the mismatch appearance and mismatch constraints condition was significantly lower than that for the mismatch appearance and no constraints condition, the mismatch appearance and no constraints condition, and the mismatch appearance and mismatch constraints condition. Regarding the movement behavior features that describe the local motion of participants, we also found a significant effect on the participant step length across the 5 experimental conditions. Pairwise comparisons shown that the mean score for the matched appearance and no constraints condition was significantly higher than that for the mismatched appearance and no constraints condition, the mismatched appearance with constraints condition, the mismatched appearance and mismatched constraints condition, and the mismatched appearance and mismatched constraints condition. Finally, no significant results were found with respect to the step duration of the participant's motion. We also conduct correlation analysis to investigate possible correlations between electrodermal activity and movement behavior. The Pearson product moment correlation coefficient was used to screen the data. Based on the conducted correlation analysis, we were able to identify negative weak linear correlations between peaks amplitude and step length, peaks amplitude and deviation, and number of peaks and step length. The obtained results from the electrodermal activity measurements showed that there were alterations in participants' arousal in the group that experienced the mismatched appearance with constraints and the mismatched appearance and mismatched constraints conditions. Our results indicate that regardless of whether participants were exposed to constraints or mismatched constraints situations, their prior knowledge of real-world obstacles exerts similar effects on participants' physiological responses. The results from emotion feature measurements indicate that from a global point of view, participants tended to move slower in the virtual environment when obstacles were located within the real environment compared to the conditions in which no obstacles were present. From a local point of view, we found that when participants were placed in mismatched conditions, the step length decreased. It shows from a local point of view how participants tend to regulate the stepping motion. For us, it looks like participants did not feel safe enough to perform long steps but rather short ones in order to move to an area close to their current position. Finally, although only weak correlations were found, the results indicate that changes in the participants' movement correlate with electrodermal activity. Our findings indicate that when arousal increases, step length and deviation of the provided depth decrease. Besides the promising findings that our study has yielded, there are a few limitations that should be addressed. The first is related to the electrodermal activity. There is a chance that the significant effects that were found when examining the results of the electrodermal activity might be random instead of regular due to the unwanted noise captured during the walking task. The second limitation is related to the way participants were depicted within the virtual environment. It is assumed that additional experimentation in which participants are represented with a self-avatar might provide interesting, quite possibly varying results. A third limitation is that for the purpose of this experiment, we examined just 5 conditions, even though we could have added more. However, we decided to limit our study to the 5 conditions since in real life it is more common to have user experience a virtual environment that is different from the real home environment in terms of appearance and constraints. The last limitation we wish to acknowledge is the omission of a questionnaire. It looks like additional self-reported emotion ratings are necessary to explore other emotional dimensions such as stress and confidence. Understanding the way a virtual reality participant's behavior changes when interacting within virtual environments which do not match the appearance and constraints of the real ones might help developers build virtual reality experiences that can be considered more precise and thus more efficient. As a result, user engagement and immersion would also improve. In this project, we studied the impact that real and virtual environment mismatching had on participants' arousal and movement behavior. The obtained findings indicate that the mismatching between the real and virtual environments indeed affect the arousal and movement behavior of our participants. However, this was more obvious when there were both appearance and constraints mismatching between the real and the virtual environments. Thank you for attending my virtual presentation.